Okay, so if in the E equals F over Q equation, the Q represents only a test charge and not the charge that sets up a field, what happens if we don't know anything about the test charge or don't have a test charge, but we want to know the electric field strength? That is, can we figure out anything about the electric field strength using only the charge that sets up the field, only the source charge? Well, sure we can. And in this video, we'll explore how to do that. Our learning targets remain the same as presented in the first video, so let's just jump right into it. So using just a source charge to figure out the strength of an electric field is analogous to finding the size of a gravitational field using only the mass that sets up that field. Like if we wanted to find the strength of Earth's gravitational field using only the mass of the Earth, is analogous to finding the size of a electric field using just a source charge. So here's how we go about doing this. We start out with a charge. This is the charge that sets up an electric field around it, and we want to know what the size of that electric field is. If we were to place a test charge somewhere in that field, we could find the size of the electric field using E equals F over Q, like we did in the last video, and the force between them using Coulomb's law. But remember, we're assuming that we don't have that test charge. But we do know that Coulomb's law tells us something about what the force on that test charge would be, and we know that E equals F over Q tells us something about what that force on that test charge would be. So we can set these two, we can solve for the force and set these two equal to each other, giving us this right here. Now in this, we have gone through and taken and made Q2, made the test charge, the non-existent test charge, Q2 in this case. So from this, we can see how Q2 will cancel out and result in our equation here for the electric field of a single point charge. Once that Q2 cancels, all that remains is Q1, which is the source charge itself. It's important to remember that in this electric field equation, this Q is the size of the charge that sets up that electric field. It's like if we were doing this for a gravitational field, this would be the mass of the Earth. Okay? So this is not the test charge that's placed in the field like it was in the last equation we had. You'll have to remember the distinction between the two in each of these equations. So let's look at an example. So here, the electron of a hydrogen atom orbits the proton at a radius of 0.053 nanometers. What is the electric field due to the proton at the position of the electron? So here would be our proton, here would be the position of the electron, here's the distance between them. In this example, we're only given information about the charge of the proton. So we apply our equation then that uses only the source charge in it to find our electric field to be 5.13 times 10 to the 11 newtons per coulomb. And now this would be directed outward from that proton. So the direction of this electric field would be out this direction. Now we can't see the electric field, so we use pictorial tools called electric field diagrams to help us visualize the electric field in a region of space. We can represent the field and the direction of the forces it will exert by drawing in lines that show how the forces would be directed. And we call these electric lines of force or electric field lines. These are imaginary lines drawn through a region of space so that the tangent to a field line at any point is in the direction of the electric field at that point. And the field lines are closer together where the electric field is stronger. They're further apart where that electric field is weaker. So the electric field around a single positive charge would look like the picture here at the top. The electric field around a negative charge would look like this one. Now remember from our electric field model that the direction of the arrows is the direction of the force that would be exerted on a positive test charge placed at that point. The lines show that any positive charge in the field around a positive charge would experience a force that would push it away from the positive charge in the center. the lines around a negative charge show that a positive test charge would be pulled toward that charge in the center. So when we have multiple charges near each other, the electric field can be pictured like this. If we have two positive charges, and if we have two negative charges, the field lines would look like this. Now here, the difference between these two is that with the positive charges, those electric field lines are pointing away from the positive charges. With the negative charges, they're pointing toward the negative charges. And if we have two unlike charges, one positive and one negative, those electric field lines would look like this here, where those field lines then are connected between the two, going away from the positive charge toward the negative charge. In this case right here, our electric field is going to be strongest between those two charges. Now it's important to remember that in these electric field diagrams, right, the electric field exists at all points in between these lines. These lines are just representations of that electric field at various points around those charges. Now suppose we want to find the electric field due to more than one source charge. Now think back to when we did this with Coulomb's law, and we had maybe a charge here and then another charge here. If we wanted to find the force then on a charge here, right, we would use Coulomb's law and find those forces, right? And that net force would be the vector sum of all the forces due to all the individual charges. Well, here we're not looking for force. We're looking for the size of the electric field. We're looking for the size of the agent of that force, say at that point right there. Well, electric field is a vector just like forces are vectors. So the electric field due to multiple charges at that point is the vector sum of the electric field due to each of those charges. So what we would have to do in that case is use our KQR squared to figure out the electric field strength from each of these individual charges at this point right there, and then add them vectorly. So the electric field from this positive charge right here is going to point in this direction here. So we'd have this electric field due to charge 1. Okay, we'll call that charge 1 and this charge 2. And then for charge 2 then, that electric field would point this direction, so here would be our electric field 2. Okay? It's going to point to the left. E1 is going to point to the left because the electric field points away from positive charges, and it points toward negative charges. So we look at those two individual electric fields, and our net electric field then would point in some direction between them. So the basic process to solving some kind of problem like this would be to use KQR squared to figure out E1, then use KQR squared to figure out E2. Then, once you have those, you would have to use vector analysis to figure out the x and y components of each of those electric fields, add up everything in the x direction, everything in the y direction, then Pythagorize everything to figure out your total electric field. Now, we'll see examples like this problem in class, but due to time constraints, we're not going to go into it here in the video. But this is the basic process of solving something like this. Okay, so that concludes this video. Next, we're going to look at what are called uniform electric fields. We're going to introduce a circuit element called a capacitor. We've talked about capacitors when we talked about Leyden jars, right? A capacitor is simply something that stores up charge. And what we're going to find is that in a capacitor there will be what's called a uniform electric field. It's an electric field that's constant throughout. There's no fluctuation like in the diagrams that we've seen. Like here, where there's areas where that electric field strength is greater than other areas, and we can tell that because of the how close the lines are together. In a uniform electric field, the electric field is constant throughout. One of the major things to remember at this point, though, is we've got E equals F over Q, which give us our electric field strength on a test charge within that electric field, and then we've also got E equals KQR squared, where this is the charge that sets up that field. All right, see you next time.